Okay, so hello, it's me again, Charlie, and I'm here with the video for E16A extra credit. More like extra review for the discussions since they're written expressly for the purposes of the exams and reviewing the concepts. So today, it's corresponding to the lectures about matrices and linear transformation and the one on the Thursday after. So this is week 2 or week 3. Um, And you can also check my other video out on matrices and linear transformations. This is basically the discussion related to that concept. So that's going to give us some fundamentals for this, so we don't have to go through many of the derivations as painstakingly. And now we can just jump into the problems. So I have the problems. So yeah, this is it's saying as I mean, you can go on to the discussion yourself and see it. I'm just gonna paraphrase it. So basically, you have this system of people working: Facebook, YouTube, Instagram, and work. And then this is your related digraph, if you will. And then so we know that the transition matrix is supposed to have this kind of formula where the next state is the transition matrix times the current state, and then how are we going to do this? Well, we have to review the definition of matrix multiplication. So this is the number at each place, right? And then when you multiply it, you have the number at this place times this column. I mean, this is just from the definition of matrix multiplication. So therefore, we can conclude that a column is simply a distribution of the population corresponding to the column. For example, this Facebook column right here corresponds to the number of Facebook, so then it tells you how many people go to Facebook, YouTube, Instagram, and work, and it's the distribution which is given to us in the graph. So it makes conceptual sense for each column to describe the distribution of the corresponding weights. Right, so then we can conclude, because of that the column is one location and it tells you where it's going to end up. So it's basically columns to rows. I talked about that in the other video that you can check out. So I'll just read that column. The first column from it is the from Facebook column, and then we can say in general that it goes to the row, and therefore we can just set it up. So this is from Facebook to Facebook is 0.4. And then so on, we can just fill up like so using the fact that it goes from the column location, which we set up in this convention, since that's how they're listed on the discussion sheet, but it could be any convention. It's just, as long as you keep that convention, it should be good. Facebook, YouTube, Instagram, work, and then you just fill it in. All right, so for B, it's basically saying this is how many are at Facebook, YouTube, Instagram, and work. And once you find the next time step, we can just simply use our convention of Facebook, YouTube, Instagram, work, fill out those numbers which were given to us. And then from part A, this is our transition matrix, right? So then we can just use the definition to find the next time state, which is this, is just multiplying it together. And when we do that, some arithmetic, row dot column, to find the ijth value of the product. And then that is our result. So that is our solution, 185, 240, 60, 265. So we can see a significant increase in the amount of people working. So, right, so I already said before that column represents a distribution of the population of the corresponding location. So if the columns sum to 1, now, what does this mean? This is what part C is asking. And what does it mean when it sums to 1? This just means that the entire distribution, which it represents proportions, well, that adds up to 1. So a whole of it remains in the system, because this matrix is supposed to model the system, right? So that means essentially every student initially in the system will stay in the system, which is comprised of this 4-part Facebook, YouTube, Instagram, and work. So yeah, note that when I say 1, it just means 100%, which means everyone, not just one person, because this is a proportions that we're talking about. And part D is on their sheet. Part D is they want to predict how many students will be on each website times n to the future? Well, we can just recursively kind of do it, right? I mean, this is just multiplying the matrix on itself over and over again. So I can use the power operator that I've also defined in the matrices and linear transformations lecture. And this tells you n time steps in the future, and you can just use one power operation. Now, numerically, one may have to, like, if you take Math 54, diagonalize it, makes it a lot easier to compute. But we won't worry about that yet. It's just, it's just, this is just a notation for us to be conceptually familiar with. So, and without working it out, 100 time steps in the future, well, if we look at the graph carefully, you'll notice that everywhere points to work, but then work doesn't go anywhere else. So after such a large n, we can conclude that they all go to work. So 100 is a large n, significantly large in this case. So yeah, I'm just going to say straight out that in 100 time steps in the future, pretty much everyone's going to be working. Now, E is just saying instead of work, it's a void, which just means we're not going to be considering anymore any of this, any of the relationships with work. Like, that just gets thrown out. So we only have a 3-component system now. All right, and then we do the same thing. We redraw the system, and then you can do that by relabeling the work as void. And then when you redraw the system, you do columns to rows, and you do it like that: Facebook, YouTube, Instagram, and then you do it just like that. You fill in columns to rows, Facebook to Facebook, YouTube to Facebook, etc. So major differences are, it's only a 3-component system now. Not everyone stays in the system, right? So they go to the void, that's out of the system. So people are leaving to go work, and then thus the note, as a corollary, the columns no longer sum to 1. And we can suppose by saying that the difference with 1, we can assume it goes to work, which is probably how they calculated it. All right, number 3, part 1. We're going to do some linear operations, geometric transformations, basically. So A is just basically saying, how I'm going to get 45 degrees if I know how to do 15 and 30. Well, first, if you rotate 15 first and then 30, you're going to get 45 degrees. Or if you do 30 first and 15, then it's still going to be 45 degrees. But because they are rotate, so in general, I'm going to say, we'll see later. But for now, in general, I'm going to say that linear operations are non-commutative. But in this case, they're just rotations, right? You can rotate in any order, and then it should be the same thing. Because, it's just, like this and that, or like that and that. There's no, like fundamental differences going on. There's still a point at the origin, for example. So I can do T1, T2, T2, T1, so that's a 30. No, that's a 15, that's a 30, that's a 30, that's a 15. In this case, I write it like that, but you do T2 first since it's closer to the V. So you rotate, in this case, by 30 first, then 15, and this is vice versa. You do 15 first. And then for 60, I can do like 15 4 times, but let's just do 30 twice, right? That's the quickest way. That's the most convenient way. And then for part B, it says only one matrix. It's T2 by T2, and it's going to have the same form as the previous, and we're going to prove it in part C. So part C wants us to show what a rotation matrix form is, and if you follow along in the other lecture, you already know that it's we'll see. So basically, we use the proof that we just simply use the transformations of the standard bases and see where they lie. So transformation of E1 and transformation of E2, what happens when we rotate them? Well, from trigonometry, the transformation of E1 is just cosine and sine, and the transformation of E2, which is 90 degree pi over 2 rotation, we can use some double angle formulas. So we're going to find that the x is negative sine now, and that the y is cosine. So we can fill that out. So this is the x components and the y components, and this is TE1, TE2. We fill that out. Now we're going to revisit it. It is true that if I do 30 degree rotation twice, if I numerically calculate it, plug in the values for cosine 30, sine 30, and then I multiply it by itself, it's going to get me, the values for the rotation matrix for 60 degrees, right? You can do it yourself, or you can do a more general proof. In this case, I did not generalize it just to show that 30 twice is 60, but really for any theta 1, theta 2, if you theta 1 and theta 2 in this case, if you did 30, let's theta 1, and like 45 is theta 2, and you want to see where it ended, you can always use the trigonometric identities. Yeah, so I mean, I'm just multiplying them out, brute force kind of, and then I find out that this is the cosine addition formula for 30. So like cosine x plus y is equal to cosine y cosine x cosine y minus sine x sine y, and sine x plus y is sine x cosine y plus cosine x sine y. And then we see that they match the patterns. You can work it out yourself if you want. It's kind of a brute proof. And I'd be willing to, I guess, explain this in more detail, but it's just trig identities essentially. Yeah, so we're not going to use inverses here. We don't have to use the method of inverses. We're just going to rotate in the other direction. And since it's a rotation, you get rotate here, rotate there. It's the same thing. That is basically the inverse operation. So we end up with what is the inverse operation, but we're not going to straight up do it. So if you rotate 60, you want to rotate the other degree, negative 60. So you plug in negative 60 here, and then we get that. Right, so basically the signs here have switched because cosine's an even function, but sine's an odd function. So only those signs would really matter. Sorry about that. Yeah. Okay. So for part E, it basically wants us to obtain the inverse rotation matrix. And what are we going to get? Well, in general, we just use negative theta for every rotation of theta because you're going the other way. And then, yeah, we find that these signs have switched, right? Because of the nature of the cosine function and the sine function. The cosine function is by nature even, and sine by nature odd. And then let's see what happens when we multiply it by an original rotation matrix. Well, obviously, as we can predict, rotation matrix by an inverse rotation matrix is the identity matrix, which means that things stay the same. So these are, in fact, inverses. Yeah, right. And then you can do it the other way around. It's still I mean, because it's the inverse, right? They work both ways. Now, for part 2, it's kind of just saying, like, let's see what happens when you rotate it by 60 and reflect it, and what happens if you reflect it first, then rotate it by 60. Okay, well, I'm assuming that they're talking about the unit square. They don't really draw on the discussion itself, but the unit square of the diagonal, the diagonal of the unit square, and then when we rotate it by 60, it's like 105, and then we rotate it, it's like over there or something like that. Or I start from here, which is the base, and then rotate it by 60. The point is they're different, right? If I reflected it first and then rotated 60, well, that's going to be more of a, like, more of a rotation. It's probably going to end up like there, said, like, of 105, then reflect. Then if I did 135, 195, well, there's a significant difference, right? As we can see if we try to start with the x-axis. So they different, and the whole point is it's not commutative. So I'm just going to do create the reflection matrix, and if you reflect over the y-axis, you'll get that because the y-axis remains untransformed, but then this standard basis becomes negative. And then I'm going to rotate 60, going to use the rotation matrix I just derived. And then I'm just going to rotate first. Then, no, I'm going to rotate first. It's right to left because it's closest to the vector that way. So rotate first, then reflect, and then I get that. And then we're going to see that's numerically different in this case than if I reflected first and rotated. In fact, both of the signs are different, so it's a different result. There's no commutativity. That is the important result. And then, we reflected the unit square twice. Where were we going to get? Well, yeah, in general, they should matter. We have proved that there is non-commutativity of linear operators. Just one way to prove that it's not true. All we have to do is find a counterexample. So in general, it's not true. But sometimes I can give maybe like if it was at 45 degrees, then I reflected it here, then I reflected it there. Well, then it ended there. And then if it's 45 degrees, and then I reflected it over the x first, it would be like that. And then the y would be like that. Y first, it would be like that. And then it would be like that. Since it's 45 degrees, it's an angle bisector. It works perfectly. But in general, no. Right? So if it was just the x-axis itself, then it reflects over the x, it wouldn't do anything. Then over the y, then it would be like that. And if it was the y-axis itself, it reflects over the y, it wouldn't do anything. And then, it's clearly, it's clearly, it's clearly different. And you can do that just by analyzing the matrices as we have for the rotation. Yeah, mystery bonus problem for E. I don't know. All right, and last one, nilpotent pumps. Basically, the system is basically just a flowing out system. So we can eventually conceptually tell that this is going to go to zero, right? Every time it's just less and less and less. So we're going to use the same transition matrix technique because this is still like a transition matrix applicable technique. We're going to get this. So this one's completely zero. The automatic blur. I don't know why that happens. Right. Okay. Okay. So the first one, the first column, we can see is all zero because they just flow out. And then the 2 goes to 1, 3 goes to 2, 4 goes to 1. And then that's a state vector, 1, 2, 3, 4. Well, okay, so that's part A. That's just a setup. But part B, what is A to the 4th? Well, I'm going to straight up say is 0 because conceptually, if I operate A 4 times, I just look at the system and I say, well, it's going to just keep flowing. There's nothing in 4 left, and then 3 goes to 2, and then 2 goes to 1, and then it's empty. After 4 turns, it's empty. Just like we can follow the arrows and kind of see that. So that's intuitive. That's intuitive physical description. Now I'm gonna like kind of more like rigorously calculate this thing. I just multiply. You can multiply it by yourself. It's kind of a brute force method, and we end up with 0. So this is what nilpotent means, right? It means so for some finite n, as long as it exists, some finite n exists, a to the n is equal to 0. The 0 matrix, right? And this makes sense because everything spills out. And what is this invertible? Well, here's my intuitive argument. My intuitive argument is that no, it is not invertible because like your thing spilled out, it's out of the system. How are you going to get it back? That doesn't really make sense. Because you can't reverse like a spill, right? Like you can't. Like where are you getting it back from? You have no information on where it went, right? When it spilled, it's out of the system, so it's out of your measurement. And rigorously, I can use the the AI proof. This is matrix A, this is the identity matrix, and then I'm trying to reduce it. There's not even a pivot in the first column, so clearly I cannot reduce this to the identity matrix. So yeah, that's the rigorous proof. And also the columns are linearly dependent because that's 0. And then there's a inverse proof in the next discussion that I'll go over in more detail about inverses. But for now, just take this. And then, so D, if we relabeled it, well, it doesn't matter because I can relabel my matrix and I get the same thing. It's still nilpotent. Like changing the order doesn't matter, right? Like I do that. I find out that, if I fill this in, it's still the same thing. And that's just changing the order. It's not going to affect the nature of the problem at all. And for E, right, so fundamentally, if I call this C, then C to the 4th is still 0, okay? And then for part E, if there's a nilpotent matrix, is it possible that B exists? Well, so more intuitive argument would be kind of like, yeah, because like if I had A is nilpotent, but then I had B in front of it, well, B to the n is like BA times BA. Well, this B is kind of buffering the A. Well, that's not rigorous enough because like, what if the AB like turned into 0? Well, I'm gonna try to prove it, but I'm kind of rigorous. It's not even that rigorous of a proof. I'm aware there's more rigorous proofs online, so I have linked one in the description to a Quora page. I hope that's sufficient. I could try to come up with a proof. It took kind of a long time, and it has to involve eigenvectors because I'm not really sure how else to phrase it. Okay, yeah, so I have to revisit this section a little bit. Sorry about the interruption. But basically, this is only for Math 54. I would feel like it's... And also, ignore this to the 4th. I'm just assuming to, like, for any A's, not the one we had where A to the 4th is 0. Let's just do N, right? So let's just generalize lambda N. V, we can just, like, inductively go down. And then we can say that, yes, the eigenvectors are 0. But for BA, I mean, while we were trying to find the eigenvectors as much as eigenvalues as much as possible, well, I mean, if we plug it in with the same eigenvector, we get that. How exactly did we get that? Oh yeah, so then we replace AV with lambda, which is still 0. So yeah, basically that is, yeah, so it's still going to have a 0, and then, so yeah, something to do with the null space with non-trivial solutions. It's not just the 0 vector, as other stuff. But then there's nothing else that says that BA has other eigen values, right? It can, and it can be diagonalized. This proof only works in the case of if it can be diagonalized. That's the problem. But generally, I'm arguing that you could create one. There's like a numeric proof that I'm not familiar with that I'll post on Quora again. So yeah, this is kind of a complex proof. Sorry about the interruption. I had to kind of relook at it, and then if we diagonalize it such that these eigenvectors are not 0 and it can be diagonalized, then every power, this will never be the 0 vector, and everything else will stay the same. So it is possible to have it not be nilpotent. Sometimes even idempotent, if these are like 1, for example. Idempotent means any power is the same. So in this case, we can just do kind of like, it looks like the inverse matrix, but it's not on the main diagonal, it's on the other diagonal. And then we kind of multiply it, and then that gets something that I'm going to call semi-idempotent, which means that it just rotates around 2 states. All right, so 2B is going to come up in a separate YouTube video, so stay tuned for that.